Hello everybody, welcome to Nuclear Reactions on Fission and Fusion. This is our lesson 16.4 via PowerPoint mostly. Just taking a look. Fission reactions. Fission reactions, first of all, are when atoms are bombarded with neutrons and their nuclei splits apart. Now each size will be roughly the same size, more or less. Now it can also happen spontaneously, where something with a high mass number just spontaneously splits into two nuclei, again about roughly equal size. During nuclear fission, neutrons will always be released, and this is one of the things that's unique or indicative of all fission reactions. So taking a look, there's two types again, the spontaneous reaction as well as the induced reaction. The spontaneous one, again, you have that very large isotope. It's unstable and just spontaneously decays. Now, instead of like alpha decay or beta decay, you're going to wind up with two nuclei roughly the same size. That's always going to be, again, accompanied by the release of neutrons. Induced fusion is when we bombard the atom with neutrons, making it unstable and therefore splitting into two equal parts, which is far more common because usually the things that are unstable tend to break down naturally anyway, and it's very tough to find and harness. Okay, again, always released by the release of neutrons. So if we've got this neutron coming into uranium-235, it strikes, captures the neutron, and thus, if you take a look at the mass numbers and the charge numbers, you're going to wind up with uranium-236, and then it splits apart because it's very unstable and splits into two equal parts. Notice that the mass and charge is all conserved within this reaction. And then they go flying off. So this is the example we just saw. Notice on the top with the reactants, you had 236, okay, 235 and 1 gets 236, 141 and 92, and 3 ones also equals 236. Remember, it's 3 ones here. We've got a 92 and 0, 56, 36, and 0 on the bottom. So it comes to 92 and 92. The other reaction, another reaction, because it's not always going to be the same, looks like this. So both fission fragments and neutrons travel at a high speed. The kinetic energy winds up being far greater than what we started with, and therefore the kinetic energy before the fission is much less than the kinetic energy after the fission. So there's energy that is being released in this case. It is the result of the fission reaction itself, and it's energy that's stored within the nucleus. Right? Therefore, a nuclear reaction. So if we want to calculate the energy from this fission reaction, this is the example that you have in your books. We've got the atomic masses of all the pieces, and so we're going to use this. First thing we're going to do is calculate all the mass that happened on the left side of the equation, the reactants, and we're going to calculate the mass of the products. So we see that there is a mass difference, that the total mass here is not equal to this. There is a difference. And so the total mass before, total mass after. So we're going to take that mass difference, which is 2.65 times 10 to the negative 28 kilograms. This mass results in the release of energy using Einstein's equation E equals mc squared. So we're going to use that equation where the mass here, this is the mass difference, mass defect, if you will. Using E equals mc squared gets us 2.385 times 10 to the negative 11 joules. Now this may seem like not a lot of reaction. Again, it's times 10 to the negative 11. However, you have to remember that this is from a single nucleus. Very, very tiny amount of matter. Large amounts will release huge amounts of energy. So if we had 1 kilogram of this uranium-235 being released, well, the number of atoms there is going to be 2.56 times 10 to the 24 atoms. And so multiplying the energy of a single atom multiplied by the number of atoms gets us 6.1 times 10 to the 13 joules. And again, this is much higher than you would see within any chemical reaction. Now, fusion is a little bit different, where nuclear fusion is where two nucleuses with low mass number combine to make something with a higher mass number, such as this one. Now, here we see this one. This is what's happening in the sun. Hydrogen 2 and hydrogen 3 forms helium and this neutron being released. But within fusion, you do not always have neutrons being released. So we've got this example here. They come together. They're going to form a product which is unstable, and then that energy is coming out with the hydrogen. We can calculate the energy in the same way we did before. Given these numbers, we're going to find the mass difference and then the energy released in fusion. Total mass before, total mass after, and we see again we have a mass difference. Now, a rather small mass difference. These numbers are not the same, but is something to be wary of. And so again, find that mass difference of 3.1 times 10 to the negative 29 kilograms. And we're going to then plug that into E equals mc squared to find 2.79 times 10 to the negative 12 joules. Again, looks like a small amount of energy, except this is happening on a per nucleus basis. Okay, let's do one more example. This time, we're going to take a look at another fission reaction, except in this case, instead of being given masses in kilograms, we're being given masses in atomic mass units. And in this case, we're seeing helium-4 and oxygen form neon-20. And so the reaction would look something like this. Okay. Now, the atomic mass units of the helium and oxygen is, when you add them together, 19.997 518 atomic mass units. Notice again that the mass that we have here and here are in fact different. And so we've got a difference in mass. This is 19.997 518 atomic mass units. And this is 19.992 440 atomic mass units. The difference between the two gets you a mass of 0.005 078 atomic mass units. Now we're going to multiply that by our 1.66 times 10 to the negative 27 kilograms as found on our formula sheet, which means the mass difference is actually 8.34 times 10 to the negative 30 kilograms. And that's what we're going to use in our E equals mc squared And we find the amount of energy here released is going to be 7.6 times 10 to the negative 13 joules. Again, doesn't seem like a lot, but that's for one atom of helium and one atom of oxygen. If we had just, like a few grams of this, we would be releasing a whole lot of energy because we would now be dealing with things in the mole, and we'd be looking at factors of a million or billion type joules. Anyway, thanks for watching. Have a great day.